So start by writing down this problem and then think about how would you approach it. What would you do in order to actually find that smallest vertical distance between the parabolas? So as you take a look at this, we're looking to find the minimum vertical distance between the parabolas. Well, first of all, just as a really quick think ahead, I'll tell you right now that if we graphed them, we'd end up looking at two parabolas going the opposite directions, but they don't cross. If it turned out that they crossed, then we'd be able to just figure out where do they actually meet each other, because the minimum distance then would be 0 between them. But as it is, they don't cross. And since we're just looking for the minimum vertical distance, that's going to make our lives a little easier as well. All right, so if I want to know the distance between two objects, that means I'm looking for the difference. So I'm subtracting. So in this particular case, I'm going to want to subtract one function from the other one. Now, it doesn't actually matter which one you do. It's just one will give you a positive answer and one will give you a negative answer, but all distances are positive, so it would work either way. But because I do like it to stay positive and stay intuitive, I'm going to start with the one that's opening upward and then subtract from it the one that's opening downward. So that means I'm going to do the x squared plus 1 minus the x minus the x squared. Now if I do that, remember that gives me the vertical distance that's between the two of them. And so I'm going to come up with a name for that. I'm going to call that d, because that's going to represent the vertical distance. And before I go any further, I do want to simplify it, so let's go ahead and simplify there. So I end up doing x squared minus a negative x squared, so that's going to be the same as x squared plus x squared, so that's going to give me 2x squareds there, minus x plus 1. I do like to keep it in standard form, it just makes my life a little bit easier. So I'm going to be looking for the minimum of that. If I want to find out what the minimum of that distance function is, because remember this function does represent the distance, that vertical distance between the two functions. If I want to find the minimum, then I can go ahead and find the derivative and set it equal to 0. So I'm going to go ahead and now find out what d prime is. So we take our derivative, that gives me 4x minus 1. I set it equal to 0 because I want to know where that minimum actually occurs. And so we end up finding that here that x equals 1/4. And a little side note on this, if you had done the subtraction the other way, if you had done this function minus this function, you would have gotten all the way down to the end here and you would have found that x equals a negative 1/4. But again, we're talking distances here between them. How far are they apart? And so we'd have to say, okay, well then that means it's a vertical, or that distance actually happens at 1/4. No, check that. This would still be 1/4. When we plug it back in, it would give us the negative instead. All right. So then let's go ahead and take a look here. Is this my final answer? Is the x equals 1/4 the final answer?
No, you need y.
Yeah, it's not. Because notice it says what's the minimum vertical distance. It's not asking where does it happen, which is what this is. This is telling us where it reaches that minimum distance. We actually want to know what that minimum distance is, so take that 1/4 and plug it back into that distance function. In other words, you want to figure out what is d of 1/4. And this is the part I was thinking of earlier, where if we had done the subtraction the other way, we'd get a negative instead of a positive, but the distance still is having to be positive, so we'd just make it positive if it wasn't. All right, and so when we do that, we get 7/8. 7/8 then is actually what the distance is. That's actually what our distance gives us, and so that is our final answer. Those two parabolas reach a minimum vertical distance between them of 7/8. And again, though, this is a vertical distance only. We aren't worrying about diagonal distances or anything like that, which is fortunate because that would make it a bit trickier. So this problem is actually an example of what we do call optimization problems, where we're trying to figure out the maximum or minimum that comes out of multiple equations, generally two equations. And so you notice I took those two equations and I combined them in some way in order to write a single equation that I was then able to find the max or min of. That's the basic idea behind these notes here. And this is reflective of also some notes that are in the book if you wanted more detail on any of these or ever getting forgetful. But the basic idea here is that you want to read through the problem because oftentimes these are going to be story problems. And then draw diagrams. So far this just sounds like normal good problem solving techniques, and really that's what this is. And then you write two equations. Now notice though, two equations. So this is basically saying that we're starting with a system of equations. So we're going back to that idea of systems of equations. It is just that once we take that system of equations and then combine them to form a single equation, we're going to find the max or min, which means we're going to use the derivative. So we're basically combining the old idea of a system of equations with the derivatives that we've been learning this year. We're going to now apply it to this problem. So go ahead and write down this problem and then we'll work it through together. Alright, and so step one in that process that we made note of here is you read through the problem and make sure you understand. Okay, hopefully we've done that now as we wrote it down. But the second step is to draw a picture if possible. Now in this case, the picture doesn't make as much sense. We're just working with basically a number puzzle here. So I'm not going to worry about drawing a picture in this case. So then, next up is to write two equations. Alright, so the first one, I have the sum of two whole numbers is 16. So I need two numbers, so that means two variables. I'm going to be uncreative here. I'm going to just use x and y. So we're going to say that x plus y must equal 16. Alright, and then we go to the second equation. It asks us in the next sentence, what is the smallest possible value of the sum of their squares? Okay, so sum of their squares, that means I have to do square of x plus the square of y. That's the sum of their squares. Now, I want to find the smallest possible value for that. And so it has to equal whatever that possible value is for that sum. So I need something that it's going to represent. It doesn't actually matter which variable you choose to represent this. That being said, a typical one that the book uses for just any old number that it has to be is q. Don't know why, just is. So I'm going to go ahead and use that here because it's just representing this abstract value of the idea of the sum of their squares. So that's what that q is representing, is the sum of their squares. So basically our goal here is to get the minimum q. So we just got to keep in mind that's our goal. Alright, so I got my system of equations. I now am going to combine that system of equations. Whenever I combine those, my goal with doing the combining is to basically take this equation that used to have three variables and turn it into an equation that has two variables. That's why we're going to use substitution. Is we're going to take this equation and substitute it in for either x or y so that we can get rid of one of those variables. Now traditionally when we've used substitution to solve a system of equations, we solve for y, so I don't see any reason to change that. So I'm arbitrarily going to choose to solve the first equation for y. So if we do that, we subtract the x from both sides. That gives me y equals 16 minus x. So then that's what I'm going to plug into the other equation. So the other equation now becomes x squared plus, and instead of y squared, it's now going to be 16 minus x squared. Still equal to the q. Alright, now I am going to try to find the minimum q, which means finding the derivative. And yes, I could do that right now, but wouldn't it be easier if we cleaned this up a little bit first? So go ahead and clean that up. And when we clean it up, this is what we should be looking at. Yes, I went ahead and wrote it in standard form just as a matter of habit. It's good form. Now remember why I did that. I did that because I'm going to have to find the derivative, because I want to find out what the minimum value is. All right, so I'm going to find then the value of q prime, the derivative of q. So that gives me 4x minus 32. Remember why I find the derivative. I found the derivative because I want to know where the minimum is. That means setting this equal to 0 and solving it. And so if we solve it, I add 32, I divide it by 4, I find that x equals 8. All right, and now that I know that x equals 8, I now can know what y would be. What would y have to be? Well, x is 8, right? And so I could actually plug that back into one of the original equations. It would definitely have to be this first one in this case. So 8 plus what is 16? Have to be another 8, right? And so then we can know that x equals 8. Y therefore must also equal 8. Does that answer my question? It's asking what is the smallest possible value of the sum of their squares, so no, we're not done yet. It's actually asking then what is the smallest value that we get for q, basically. Okay, so I need to actually plug those back in, so I'm going to do 8 squared plus 8 squared equals the sum of their squares. And so that's going to be 64 plus 64, which is 128. That is the smallest possible sum of their squares. And you'll notice in this problem, x and y ended up being the same. You'll find there's often many of these problems where we're trying to minimize or maximize something that they will end up being the same, but it's certainly not always. It's certainly not what's going to happen every single time along the way. All right, and so for this problem, this is another one where we're going to have to use that optimization problem procedure, where you're going to write a system of equations, combine them, and then find either the max or the min. One thing to clarify here, just to be super clear, we're looking for the smallest possible product. That's total. We're not looking for the closest to 0. We're just looking for the smallest possible product that we could get. All right? All right, now let's take a look at how we would set up that system of equations, that first step you need to take. Notice there are actually two different operations in this. There's a difference. And so that tells me I got to do some subtraction in this problem. And again, I'm going to be uncreative. I'm going to go ahead and use x and y. So I'm going to say that x minus y has to equal 100. Okay, and then I'm looking for the smallest possible product. Okay, so that means if it's going to be a product, I have to multiply them. So that means I have to do x times y equals some value. And again, I can name this whatever I want to. I'm inclined to maybe use p for product, but just because I used q on the last one, I'm going to go ahead and use q again. But if you choose to go with p, that'd make total sense. I actually like that. And so that's our system. That on your next line, you then will combine into a single equation. And when we go to make this a single equation, remember, I'm always plugging into this equation. The one that has 3 variables in it, I'm trying to make it into something that just has the 2 variables in it. So I'm going to take my first equation, and I'm going to solve it for either x or y. Again, it doesn't matter which one you do. Just for fun in this case, and partly because it's easier, I'm going to go ahead and solve this equation for x. Mostly just because it means all I got to do is add the y to both sides. It's a little bit easier to do. So that gives me y plus 100. So if I substitute that into the second equation then for x, that gives me y plus 100 times y equals q. And again, I want to make my life a little bit easier for the steps to come, so go ahead and distribute that y in there to make it into y squared plus 100y. All right, so we found our function. So what? What do I do with that? We find our derivative. Because I'm wanting to find the max or min, and so that tells me find the critical numbers by finding the derivative, set it equal to 0, and solve. And so when we actually set this equal to 0 and then solve it for y, we find that our y value here is a negative 50. Remember, we're just looking for the smallest possible product, not the closest to 0. In this case, our q function here, if we were graphing it, we'd actually be seeing it cross the x-axis, which is why if we were just looking for it to equal 0, or be closest to 0, then it actually would be 0. But we're actually looking for the small. So basically we're looking to see what's that value down there. All right, so now that I know what y is, I now need to know what x is. So take the y value that you just found and plug it back into that first equation. And so we find that x equals a positive 50 here. All right, is that my answer? Have I done enough to find the answer here? Always check back in the problem. It says, find two numbers whose difference is 100 with the smallest possible product. So it's actually asking us to find the two numbers. We've done that then. So then I would say that my answer is negative 50 and 50. If I want to provide any more detail, I could go ahead and multiply those and say for a product of negative 2,500. But strictly speaking, this problem didn't require us to give that extra little bit of detail, but of course it never hurts. All right, and so we've seen some basic abstract mathematical ones so far. We started with the two parabolas. We're looking to see how close they get. Then we've done two basically just number puzzles. It's kind of just to see the process in action. Now we're actually going to do a more context-oriented problem. And since we're dealing with a system of equations and we're trying to find a max or min, I think we're legally required to give you a farmer and a fence problem. We must be, because it comes up like every year, right? That you're trying to figure out a farmer enclosing a field with a fence and all stuff like that. Well, we're doing it again here. Go ahead and write down this problem and start thinking through how would you approach it. All right, so we have the farmer, we have his field. Step one, read through and understand the problem. Hopefully you've done that as you wrote it down as well. Step two, we haven't really found useful in some of the previous problems, but in this one it's going to actually be really useful. Step two was to make a picture. And so we have a rectangular field. All right. And he wants to divide it into 4 sections with 2 fences. Now there's different ways to divide it up into 4 sections with 2 fences. But notice we're told very specifically here that we wanted to go with those extra fences for them to be one parallel to each side of the rectangle. So that means I need one parallel to those sides, and I need one parallel to those sides. So this then is our way that we end up dividing it up into the 4 pieces. Now you'll notice that since this is a rectangle, that we actually have a lot of lengths here that are the same. For instance, each of these lengths are all going to be the same length. Now I need to give those a name, that length a name. I can either go with X and Y again, or I might go with like L and W for length and width. What do you think? What should we go with here? Well, it could go either way, but yeah, let's go ahead and go with length and width then. All right, so then I will call those blue lines L. So each of these vertical lengths I'm going to call the length. Then each of these 3 lengths of fence, they're also all the same length. So those are also all going to be the same. I'm going to call that the width. So each of those 3 is W long. All right, so now that I have my picture, I can go ahead and start going and writing the system of equations. All right, so first of all, we want the area of this whole rectangular field to be 900 square feet. Okay, so for area, that means we're going to do length times width. And that has to actually equal 900. And then we have the lengths of the fence. And we want to minimize the total length of the fence. So that means I need an equation here that represents the total length of the fence. To represent the total length, since I use little l and little w to represent the individual lengths and widths, I'm going to use a capital L to represent the total length. Oftentimes we'll use capitals to represent like a total or a bigger idea, and the lowercase represent an individual one. Yes, they are different if the capitalization is different. All right, so the total length then would be all of the L lengths. So we got 3 of the L lengths, right? So that's going to be 3L plus the 3 W lengths. So that'd be 3W. And then that gives me my system of equations. Now that I have my system, go ahead and now combine those 2 into a single equation. So the first equation, I need to solve it for either L or W. Doesn't matter which one. I'm going to go ahead and solve it for L. Partly because I know a few of you, when I put in a lowercase l and an uppercase L, all of a sudden you whimpered a little inside, because then we had both. So this will get us down to just one of them for the time being. So then little l would equal 900 over W. So that's what I'm then plugging into the second equation. And so in the combination here, I plug that value for L in for L to get that equation. And then, yeah, we can simplify that a little bit before we go on, right? And so if I simplify just by distributing in the 3 there, this is what I'm looking at. But the next thing is I need to take the derivative. Now when you take the derivative, you got a couple different options in terms of how do you take the derivative of this part of it here. One option is that since it's a fraction, you can use quotient rule. I don't want to use the quotient rule unless I have to, though. It's big, it's complicated, and a bit unnecessary, at least in this particular case. Because over W, remember, we can write that a bit shorter. This 2700 over W, well, I'm going to go back. I'm going to change that, since I'm now going to take the derivative. I'm going to write that instead as 2700 W to the negative 1. That's going to be a bit easier to work with then for finding the derivative. All right, and then once I found the derivative, set it equal to 0 because we're trying to find, again, a maximum or a minimum. In this case, a minimum. And in order to solve it, I think it's going to be easier by taking that W to the negative 2 and writing that as, again, the fraction. So I'm going to make that negative 2700 over W squared, just because I think that's a little bit easier to work with that way. And so if I subtract the 3 from both sides and then multiply both sides by W squared, I have negative 3W squared equals a negative 2700. Then go ahead and divide both sides by negative 3, which gives me W equals 900. And so W equals plus or minus the square root of 900. Now what's that tell us here? Well, first of all, is the square root of 900 a nice, pretty number? Yes, it is, actually. The square root of 900 is 30. All right, and then we got the plus or minus then 30. But are both of those actually possible answers? Well, could we have a length of fence that's negative 30? That wouldn't make sense, right? So then that means that I can go ahead and get rid of the negative option and just go to 30. All right, so now that I found W, I want to go ahead and now find L, lowercase l. So if W is 30, what does that mean L needs to be? Again, you could find out by plugging back into this original equation here. So you'd have L times 30 equals 900, divide both sides by 30, and L equals, hey, 30. It tells us that the field should be a square, basically. Which, if you remember the farmer and the field problems that you've seen in the past, you probably saw one before where we were trying to figure out what orientation would give us the smallest possible length for a given area, and we found that it was a square anyway. But this at least lets us see another application of that. And you'll see it gets more complicated with different variations of this. All right, before I get totally done though, I want to check and see, have I answered the actual question? Well, the question was, how can he do this, that is, set up his fences, to minimize the total length of the fence? Well, basically we have done it then, because we found that he needs the total outside dimensions then to be 30 by 30. It didn't ask us what is the total length of the fence, so we don't need to find that, although you could. It just asked us how do you need to set it up, and so a 30 by 30, what was this in feet? 30 by 30 foot square would give us the best result.